Yeah, absolutely.
Perfect. So, welcome everybody to the first meeting of our seminar. So, maybe a few words about how we proceed. So, if you want to ask the question, please unmute yourself and ask. It's very difficult for people, for speaker to see the chat. I will try to monitor it, but the easiest thing is just to unmute yourself and ask. So seminar will run weekly. So there is a homepage, probably you all already know, where I post the abstract and title of future talks. So there would be a recording if you miss the seminar. So I guess that's it. It's really welcome everybody, and it's great to see lots of familiar faces and names and some new ones. It's a great pleasure to start to kick off this spring our series with a great speaker, Jozef Skokan from London School of Economics. And Joseph will talk about beyond chromatic thresholds via combinatorial convexity. So please, Joseph.
Thank you very much, Benny, and thank you everyone for joining the seminar. So what I'm going to talk about is based on the joint work with Hongliu Chong-Shangwan and Zhixian Xu. And all of this started to happen when we all met at IBS in Korea. So let me start with a small prelude and let me pose a question, okay? And the question is that which conditions guarantee a graph G to have a bounded complexity? Now, there are two bold-faces words over here. So what do I mean by bounded complexity? And of course, what conditions I want to impose? So for me, at least for this talk, bounded complexity will mean that the graph will have a bounded chromatic number, because that means I can decompose the graph into bounded many independent sets. And because of this, and because always it is the case that the size of largest clique is bounded by a chromatic number, assume that my graph G is triangle-free, clique, then of course I'll have a bounded chromatic number. Nevertheless, this is not enough to conclude that I will have bounded chromatic number, and we still need an additional condition. Why is it so? The reason is that there exist several families of triangle-free graph G whose chromatic number grows to infinity. So let me give a few examples. So the first one is a so-called Michelski graph, which is a recursive construction which starts, for example, from an edge, and at every step it takes the previous graph and makes it to a larger, and it will have two properties. It will preserve triangle freeness, and at every step you increase the chromatic number by one. So clearly, these graphs will have an unbounded chromatic number, despite the fact that they are all triangle free. Okay, and this construction comes from really structural graph theory. Another example comes from topological algebraic graph theory, and it is called so-called Kneser graph. So Kneser graph consists of a subset of n-element set, and two sets are adjacent if they are disjoint. And well, one can easily see that if R is suitably chosen, then this will be a triangle-free graph. And it takes some effort, but again, if R is chosen carefully, then the chromatic number of Kneser graph will grow slowly to infinity. And finally, and there is another family coming from probabilistic graph theory. We take our favorite Erdős-Renyi random graph G and P. We choose P properly, and then we manipulate our G and P. And after all of this, we can get the graphs, well, with arbitrarily large curves and large chromatic numbers. So in particular, they will be triangle-free. All right. So Okay, now we see the problem and we will need some additional condition. So what kind of conditions? Well, it depends whether you are in the structural graph theory, where you might impose some prohibited induced subgraph and then study chi-boundedness. But for us, we are extremal graph theory, so our favorite condition will be sort of density condition, right? We would like to discuss what sort of density conditions guarantee that a triangle-free graph G to have a bounded chromatic number. And this is really a proper start of this talk. So I will attempt to do three things. We will briefly, or not so briefly, discuss chromatic thresholds. Okay, so that will be sort of graph theoretical take on the density conditions, why certain conditions are imposed. And then I would like to a little bit explore connections between chromatic thresholds and discrete geometry. That's something that we actually did in our papers. And then hopefully time permits me to discuss homomorphism threshold and other extensions of chromatic thresholds. All right. So we start from the classics. We start from the Mantel theorem, proved by Mantel in 1907, which says that if we take any triangle-free n-vertex graph G, then it must have average degree at most n over 2. Well, this is well-known theorem. It is also well known that there is a unique maximizer, okay, and this is complete bipartite graph, which is balanced, and that has the largest possible average degree. So let me rephrase this theorem a little bit. So I'll rephrase it in the following way, that every n-vertex triangle-free graph G, whose average degree is at least n over 2, is bipartite, and that means that it has bounded chromatic number, right? Its chromatic number is at most 2. Now, this is statement exactly one graph, k and half and half. Nevertheless, it will really start to, it really demonstrate what we are trying to do. So we try to put some condition on average degree, and we try to gain a bound on chromatic number. All right. So this theorem has a stability version proved by Erdős and Simonovic in 1966, which says that if triangle-free graph G has average degree slightly less than n over 2, then it's necessarily close to bipartite. Okay, so that means in added distance, I can remove a little bit of edges and I get a bipartite graph. But does this really mean that chromatic number is bounded? Well, and the 2-second thought says that, well, this is really not the case. And the reason is that chromatic number is very prone to a noise. So here is an example. We take a graph in which 99% of vertices are perfect, meaning they are in the complete bipartite graph, such that each of these partition classes is close to n over 2. Okay. And this will make the average degree really close to n over 2. However, I can add to it a small noise, small additional graph, let's say one of the 3 constructions that we had, and this will cause that such a graph has a high chromatic number. Okay, so we have a problem here. Well, we cannot conclude that our chromatic number is bounded. And what's the reason? Well, the reason is that the graph, the small subgraph of this graph, with high chromatic number, has vertices of very small degree. Okay, and this is a problem. So the average degree is not good for us, but the correct measure should be the mean degree. Okay, so instead of average degree, I should look at the mean degree, and that would destroy at least this example, right? All right. So This was observed some times back. So in particular, András, Erdős, and George in 70s proved that if we have a min degree at least 2n/5, then if the graph is also triangle-free, it must necessarily be a bipartite. Okay, so you can see immediately that the min degree condition allows me to go from n/2 to 2n/5. Okay, now this result is optimal. Okay, if you take a balanced blow-up of cycle on 5 vertices, which is demonstrated over here, it has min degree 2n/5 exactly and has chromatic number equal to 3. Okay. So the question is how much below n/2 we can push. In other words, if I have a triangle-free graph G and my min degree is bounded from below by something, I would like to conclude that I have a bounded chromatic number. Okay. And this yields to definition of chromatic threshold. This is due to Erdős and Simonovic, who asked for chromatic threshold for fixed graph H. And this is as small as alpha, such that if you take H3 graph G with minimum degree condition to be at least alpha n, this should necessarily imply that the chromatic number of graph G is bounded by the constant. But the important thing here is that this constant depends only on excluded graph. In our case, it would be K3, and the alpha from this min degree condition. Okay. Now, this definition is long and has a bunch of quantifiers, but its meaning is essentially the following. If you take alpha, which is strictly larger than this threshold, then we get a bounded chromatic number. And if we take alpha strictly smaller than chromatic threshold, then there must be graphs which are H3 such that the chromatic number grows to infinity. All right. So let's look at this chromatic threshold. So this problem has a very rich history. It was studied specifically for triangle. It was also studied for cliques, and the work culminated in a paper by Allen, Bocher, Griffiths, Kohakova, and Morris in 2013, who essentially gave or completed the theory of the chromatic threshold, if I want to say really that strongly. There is much more, but I really don't want to make this talk a survey talk. I would like to go to somewhere else. So I will again just look at the triangle-free graphs, and I will go straight to work on Thomassen in 2002. So Thomassen proved that if the min degree is bigger than 1/3 n, then chromatic number is bounded, 1/3 plus something. And this immediately shows that the chromatic threshold of K3 is bounded by 1/3. All right. Now, that was an upper bound, but when we want to establish equality, we need an example of the family on the graph, whose min degree is slightly below n/3 and whose chromatic number goes to infinity. Such graphs were constructed by Heinel in 60s using the Kneser graphs. So let me just elaborate on them a little bit because it's very instructive and they are also important. So what's the construction? So again, the graph will have sort of two parts. One will be kind of the perfect. So on the left, I will have a complete bipartite graph where one side is nearly n/3, the other side is nearly 2n/3, and it's complete in between. Okay. And on the right-hand side, I will introduce the noise that will force chromatic number going to infinity. And well, I will preserve the mean degree. All right. So what do we do? So on the right-hand side, we put in a carefully chosen Gneser graph, okay, with parameters m and m over 2 minus k. So m is the sign of the ground set. M over 2 minus k is the size of the subset. Our m will be much larger than k, and this will force this graph, this Gneser graph, to be triangle-free, and its chromatic number, and hence the chromatic number of whole graph, to be at least as big as k. Okay. All right. So this is about the graph over here. How do we combine these two together? So we pick arbitrary set or arbitrary vertex, which is a set in the Gneser graph. And in the central set, which has roughly 2n/3 vertices, we divided it into m sets of roughly equal sizes. Okay. And then how do we put an edges between a vertex x here and the set s here? Well, we check whether vertex x, or we check the index j of the subset in which vertex x is. If this index is in set S, then I put an edge in between. Okay. And if you give a moment of thought, that it will tell you that the density over here for this parameter, sorry, not the density, but the mean degree will be roughly n/2. All right. And of course, sorry, and yeah, I didn't create any triangles because this was an independent set. Okay. And now we come to a question. Can we say more about this for triangle-free graphs? Okay. So can we say something about the chromatic number when we are below this chromatic threshold? Okay. So we see an example when this chromatic, we saw example of families for which chromatic number grows. Nevertheless, can we say still something about chromatic number for some other families of triangle-free graphs? Okay. And can we replace bounded chromatic number with something else? And so we would like to address this question. But before we do so, I would like to then switch a little bit to some concept from discrete geometry, which was essential to us to actually address these two questions. Okay, so now we will switch to something completely different. All right, so I will now recall some nice and well-known and classical statements from Euclidean convexity. And the first one will be a Radon lemma. So this is a statement about the sets in RD. And the lemma says that if we take any set of at least D plus 2 points in RD, then there must be a partition of this point into two sets, A1 and A2, such that their convex wholes intersect. Okay, so this is statement proved by Radon in 1921. Okay, and here is an example why this works in R2. Okay, so if you have 4 points in R2, they are either in a convex position, and then over here we see the decomposition. So we take the two diagonals of this convex gon, and they must intersect. Or these 4 points are not in a convex position, but then one must be in the convex hull of the remaining three. Right? And now, okay, the statement of this lemma is optimal. So this D plus 2 cannot be replaced by D plus 1, as simplex shows. So for example, if D is equal to 2, then if you take these 3 points, you cannot split them in such a way. All right. Another very nice and interesting theorem is the Helly theorem. Again, this is a theorem about the convex set in the RD. So it says that if we take convex set C1 through Cn, and n is at least dimension plus 1, then the following is true. If all d plus 1 tuples of these sets have non-empty intersection, then all of them have non-empty intersection. Okay? So let's illustrate it maybe how does it work in R1? Okay. In R1, it says that, okay, if I have at least two sets such that any two of them intersect, then all of them must intersect. So it's depicted over here. If you take any of these 5 sets, any pair from them, that they intersect, and hence this is example of the common intersection of all of them. Okay, it's actually a very nice and interesting exercise to prove it, at least in R1. One can have a fun with it, that it's true for every n. Okay.
So in R1, so convex set is just interval, right? Maybe good to say.
Yes.
Right?
Yeah, very good point. Yeah, convex sets in R1 are intervals, so that's why it's depicted this way. Okay. So d plus 1 is again optimal. Okay, so for d is equal to 2, here is example of the 3 sets such that every 2 of them have non-empty intersection. Let's pretend they are really convex despite my drawing, but as you can see that there is no common intersection of all 3 of them. Okay, and this is example of a local global type of the results that we will see through this talk, that we have sort of local conditions where we just check locally some information about the tuples, and we want to deduce something global, right? In this particular case, it will be that they all intersect. All right, so one can do more here. Okay, so there exists a fractional Halley theorem, and it says the following. Again, I have a convex set in RD, and I need to have at least d plus 1 of them. But now no longer I will have information that all of them, all of the d plus 1 tuples of these have non-empty intersection. I will only know, let's say, that only 99% of these d plus 1 tuples have a non-empty intersection. And then, okay, no longer I can conclude that all of them have a non-empty intersection, but still this theorem allows me to conclude that at least a beta proportion of all of them have a non-empty intersection, okay? And here the important fact is that this beta only depends on alpha and d. Again, it's a local global type of the result. The theorem is true to Kachalski and Liu, and it's, well, now nearly 50 years old. Okay, but it's again very nice kind of the result. So moral of the story is, if alpha proportion of d plus 1 tuples have non-empty intersection, then at least b sets, beta n sets have a non-empty intersection. Okay, and if alpha is equal to 1, then beta is equal to 1 as well. All right. Can one say anything more, right? Okay. Yes, one can say something more. This is called this so-called PQ theorem. So we say that the set C1 through Cn satisfy the PQ property if every p tuple of this set contains an intersecting q tuples. Okay. So if p is equal to q, then we are just saying that every p tuple is intersecting. But if p is much larger than q, it just sort of tells you that you will look at the p tuples. Maybe not all of them intersect together, but there must be a Q tuple which is smaller, but which is intersecting. Okay. And perhaps surprisingly, the following is true. That if you take P at least Q at least D plus 1, then you can find a universal, oh, sorry, not universal, you can find T that only depends on P, Q, and D, for which the following is true. If you have, again, convex set C1 through Cn in Rd, which satisfy PQ property, okay, then you can find a set of T points that intersects every set Ci, okay? So let's think it one more time through, okay? So I have a system of sets such that if I take any p tuple of them, I find q of them that intersect, has no entry intersection. And when this is true, I can find independently of n t points such that this set pierces every Ci, has non-empty intersection with every Ci, okay? The result is due to Alvin Kleitman, but the main thing is that this sounds pretty powerful. It was conjectured by Harviger and Deberner in 1957, and this is really amazing theorem, right? If you go back over here, okay, if you sort of look at this statement, okay, so I know that alpha proportion of D plus one tuple has non-empty intersection. So I have a B and Z which have a non-empty intersection. Okay, so I have one point that meets all of these beta and Z. Okay, and then you might want to remove this set and iterate the whole thing. And even if everything works as it should, okay, because of this iteration, each time you gain beta proportion of remaining set, you probably need almost logarithmic many points to meet all of them. Okay. So this one, okay, asks for a bit more here, but then the outcome is worth the money because really you just need finitely many points to meet all the sets. Okay, all of these sets. Okay. So now I would like to sort of rephrase this PQ theorem in a hypergraph language. So a hypergraph, it's a pair that consists of set of vertices and a set of edges, okay, which are just sets of points. And the transversal number of this hypergraph, tau of h, is the smallest number of vertices that meets all the edges of hypergraph H. Okay, sometimes we said intersect, sometimes we say pierce, sometimes we said meet, depending on the context. So on this particular example for this hypergraph, okay, you see that every two edges have a common point. Okay, but there is not one point that meets all of the edges, and you need 2 points that meets all of them. And there are these two, and that shows that the transversal number of this hypergraph is equal to 2. Okay. So, okay, so how would we rephrase PQ property in this language? So our vertices V will be the points in RD. The edges of the hypergraphs will be our convex sets, okay, C1 through Cn, okay. And the PQ property, okay, for every P edges, there are Q of them containing a common point, okay. And then the final point will be that if I want to talk about PQ theorem, it tells me that if I have a hypergraph with PQ property, it has bounded transversal number tau of h. Okay, this tau of h in this particular thing would be bounded by this t from the theorem. Okay, so what's interesting here? So if our hypergraph H has P2 property, then it tells us that its matching number nu is at less than P. So first of all, what is the matching number in the hypergraph? It's the larger set of non-intersecting edges, okay? And so we know that if we take here p edges, then there must be two of them intersecting. So that means you cannot have a matching of size p. And so that means that this matching number must be bounded at p. Okay. And so what we would like to think about is the following question. Well, if I have a bounded matching number, nu of h, perhaps I can bound a transversal number tau of h. And it was true in the geometric setting, right? So it was true for this theorem. So maybe we would like to a little bit investigate for what kind of hypergraphs we can find a statement like this. Okay, now when we want to discuss the relations between nu and tau, we have a one trivial bound. Well, nu is always bounded by tau, because if I have a set that meets all the edges, then I have to have a separate point of every edge in the matching. So this will give me this inequality. Well, but the problem here is that this gap between these two numbers can be arbitrarily large. Okay. And so what one does if you want to say something more? Well,
But the gap is just uniformity, right? That's why it's arbitrarily large, right? So if I take a matching number, every edge is of size r, so then r times matching number would be,
yes,
but the r can be big, right? In your case.
yes, yes, precisely. Okay. So, what is this LP relaxation? So both matching number and transversal number can be written as transversal number and matching number of hypergraph can be written as a linear program. So, for example, tau of h is a minimum of sum of f of v, where v goes through the vertices of the hypergraph, where this f is a function from vertices to set 0, 1, such that for every edge in my hypergraph, sum of the value of fv over the edges is always at least 1. So essentially, we want to, this f will be the indicative function of the set that meets all the edges, okay? And I can similarly define the linear program for the matching number, okay? And okay, we have this problem. So the standard way is to consider the fractional version of these two parameters. So how do I get the fractional version? Well, I will consider functions which map vertices in particular not to the set 0, 1, but to interval 0, 1. Okay, and that will just tell me that sort of a vertex will only cover a fraction of the edge given by this f. But again, I want that altogether the vertices of the edge cumulatively will cover this edge. Okay, and similarly we can define fractional version of the matching number. And okay, so one program is dual of the other one, and that's why we get that these two fractional matching and cover numbers are the same. That comes from LP duality. And of course, here we ask, we have a bit bigger freedom here, so we get this inequality. And here we have a less freedom, so we get that inequality. So we have this natural order of these four parameters. Okay, and so the question is whether we can, because these two are the same, how much we can control the gap between these two and how much we can control the gap between these two. Okay, So I would like to know whether I can sort of make tau of H bounded by some function of the nu if I assume maybe some additional condition on H, something as the P2 property, right? All right. So, okay, that's an idea what I would like to do. The question is whether I can do it. All right. Okay. We postpone it for a bit, so I need to mention uh, uh, two more concepts. So one is something called the weak epsilon net. So epsilon net will be an approximation of a set by a simpler one. So the formal definition is that if we have a set X and we have a hypergraph on this set X and some probability distribution mu on all possible subset of X, then for this setup, a set N subset of X is epsilon net for hypergraph H. If for every H in hypergraph H, such that this probability measure of A is at least epsilon implies that N intersects A. Okay. So this really just says that epsilon net is a transversal set for large set when large is defined by this probability distribution mu. Okay. Okay. I mean, it will play a role for us. Okay. And maybe we will see soon. So the final concept that I need to introduce is something called VC dimension. So the Chervonenkis or VC dimension is a measure of complexity of the set system. So its formal definition is that for hypergraph on set X, a subset of X S is shattered by this hypergraph if the set of all intersection of S with H gives me all subsets. Okay, so if I intersect S with the edges of the hypergraph, I get all possible subset of set S. Okay, so if this is the case, such as set S is called shattered by H, and we define the VC dimension of H as maximum size of the set, which is shattered by this hypergraph H. Okay, so we try to find a larger set for which if we intersect it by H, we get all possible subset. So that's our complexity measure. And why this is important? Well, because okay, if we have a hypergraph with VC dimension D, then on one hand, we know that this transversal number is always at least as big as fractional transversal number. But under this condition of bounded VC dimension, we can also show the upper bound. Okay, we can show that this transversal number of H is bounded by some absolute constant times dimension times fractional transversal number times logarithm of transversal chromatic number. Okay, so in other words, if I have a bounded VC dimension, then I can squeeze transversal number between fractional transversal number and the function of fractional transversal number. So, okay, in some ways, okay, I'm working towards this goal, bounding integrality gap. I mean, it's not yet function of the nu, but it's a function of this tau star. Okay. And then the final thing that I need to mention is something called the abstract convexity space. So this is just the generalization of Euclidean convexity space. So this is a pair of X and script C, such that X is a non-empty set. C is a subset of the edges. A subset, it's a collection of subsets of X. It needs to contain empty set and the whole universe. And it must be closed under intersection. So in other words, if we take any two sets in C, then their intersection must be also in C. Okay. And this concept generalizes Euclidean convexity space because in Euclidean convexity space, the intersection of two convex sets is still a convex set. Okay. So for us, this definition of abstract convexity space is important because we will phrase certain our result in this particular setting. Okay. So with all of this hopefully in mind, we go back to our chromatic threshold question. So we already seen the result of Thomasson's that if graph G is a triangle free and has mean degree strictly bigger than n over 3, then the chromatic number is bounded, which shows that the chromatic threshold is bounded by 1/3. And we have a construction that shows that this is really optimal. So our question was, what can we say? What more we can say? And so here comes the point when VC dimension comes into play. So it was observed by Luczak and Thomassen in 2010 that if additionally we impose that G has bounded VC dimension, okay, then we can drop degree condition below.
Just clarify, to say that graph has bounded VC dimension, you mean the neighborhoods of the vertices, right? Have
Yes.
set system bounded VC dimension, right?
Yes, precisely. So graph has VC dimension, as Benny said, that if we take the system of their neighborhoods, then this sort of hypergraph has bounded VC dimension. Okay, and if we impose that this dimension is bounded, then we can drop mean degree condition just to linear in n. Okay, so it can be it can be any epsilon n, and then this chromatic number still remains bounded. Okay, so the quantitative version of this theorem is that if the mean degree will be at least epsilon n, then chromatic number is bounded by this function. Okay, so one can really quantify. Okay, it then allow them that to also conclude that okay, if you are really at n over 3 threshold and you are triangle free, then really your maximal degree is bounded by a constant, and they gave a specific number, right? Okay. This should be sort of, if you are strictly bigger than n over 3, then chromatic number is bounded by 4. But if you want to have this equality, okay, they had to work much harder to get this particular constant. And it also allowed them to say something below n over 3 threshold. So it allowed them to go to minus b. Okay. And then they obtain the chromatic number is bounded by constant or by linear function in this b, whichever is a bigger one. Okay. So you have some information about growth of chromatic
Joseph, just maybe to understand, right? So,
Yes.
so the way how it comes to chromatic number is that if in this graph so I have a covering set for neighborhoods, it means I have a bunch of vertices that every other vertex is a neighbor of one of them, right?
Yes.
And then since every neighborhood graph is triangle free is independent set, this is a coloring, right? This is really,
Yes.
I do the colors.
Yes.
Right?
I think I will actually come
You
back
will
to it.
talk about. I see.
Yes. Yes. All right. All right. So let me just present the first thing that we actually proved. Okay. So we proved actually that if you have a triangle free graph in which every two non-adjacent vertices have codegree, so that means set of joint neighbors of linear size, then the chromatic number is again bounded by the constant. Okay, so this is another take. So we don't assume bounded VC dimension, but we assume that every two non-adjacent vertices have many common neighbors. Okay, we call such a graph ultra-maximal triangle-free. Okay, and one can show that every triangle-free graph whose chromatic number is strictly bigger than plus epsilon n is ultra-maximal triangle-free graph. And that means that our result also implies this Thomassen chromatic threshold, but it also gives us something about information what happens below the threshold. Okay, so we don't need the VC dimension, although we use VC dimension in different contexts in our proof. But again, it just tells you that if you know that non-adjacent vertices have many common neighbors, then you know that they must have a bounded chromatic. All right. All right. So what did we do here? So given our graph, what we do is our set X will be the set of maximal independent sets in graph G. Okay. And we consider the hypergraph beta whose edges KV are indexes by the vertices in our graph G. Okay. And the set or edge corresponding to vertex V will consist of all independent sets containing vertex V. Okay. We will also need a convexity space C, which will be the intersection closure of beta. So we take all possible intersection of sets in beta. Okay. And here, important things is to realize what Benny just says, that the tau of beta is equal to chromatic number. Okay. And also that the matching number of this hypergraph beta is a clique number of G. And what we really want to get is that this tau of beta is bounded by the constant. Okay. So the way how we do it, okay, is that we prove that if our graph is this ultra triangle free, okay, we need to deduce some properties of this graph. We have to show that there is no large half graph, which then implies that there are no large bipartite induced matchings. This will give us some information about the VC dimension of this hypergraph P. Plus, we need to work harder to get some additional statements. And then cumulatively together, it will give me this R2 theorem for this hypergraph C. Okay, that means I will be able to bound the fractional I always forget fractional cover number, and that will allow me to do the bound on the chromatic number. Okay.
Can I ask a question?
Yes.
So there is this general result for convexity spaces that under some conditions, they have PQ theorems. So what you do, you're proving that your particular example is a convexity space of the type, and then you can use this PQ theorem.
That's correct, yes. All right. I realize I have still 8 minutes, right? Or less. You said 50 or 55? Let me just, yes. So let me just talk quickly. Hopefully I will manage. Okay. So this is well, maybe what else can we say? So we also can provide some insight to homomorphism threshold. So homomorphism from G to H is a mapping from vertices of G to vertices of H that preserves adjacency, right? And so we have a nice example over here. So it is a simple observation that G is homomorphic to complete graph on T vertices if and only if chromatic number is bounded by T. Okay. Now, if we talk about chromatic thresholds, then what we do in that type of question is we ask for a bounded homomorphic image because we want to bound chromatic number. In homomorphic threshold question, we ask for more. We ask for a bounded homomorphic image that retains property from original graph. So in our setting, we want to find homomorphism from K3 free G to K3 free H, and the size of H must be bounded. So we ask for more. So one would sort of think that the threshold should be higher. So we can define a homomorphic threshold that capture this property. So again, we want to find the smallest alpha such that there exists a universal H-free graph S such that every H-free graph G with minimum degree at least alpha n has homomorphism to this graph. Okay. So surprisingly, Luczak in 2006 proved that these two these two thresholds for K3 are actually equal to 1/3. And so the question is why these two coincide, right? So I'm here really asking for much more than over here. Okay. And so we try to look into this question, and that was really the starting point for us. So Luczak and Thomassen proved that if we impose a graph has bounded VC dimension, okay, then we can drop min degree to any linear epsilon n and still kept the bounded chromatic number. So while we have that chromatic threshold of K3 is 1/3, if we impose additional thing that the graph has VC dimension, the chromatic threshold drops to 0. Okay. But it turns out that if we look at homomorphism threshold, then this is equal to 1/3. But VC dimension has no effect because even if we look at, sorry, one more time. If we impose VC condition, it will have no effect on the homomorphic threshold. And the reason is that the extremal graph showing that the homomorphic threshold for K3 is equal to 1/3 have bounded VC dimension. Okay, so no change here. Okay, so what is it then? Okay, well, and here what we prove is that, okay, again, if we take this triangle-free graphs in which any two non-adjacent vertices have a linear codegree, then G is a blow-up of bounded size K3 free graph. Okay, so it's a perfect blow-up. There is no blemish or anything. We really got that this is bounded size K3 free graph. And this implies that these two thresholds are the same. And maybe it indicates that the codegrees are cause of blow-up and this homomorphic threshold. And VC dimension is a cause for chromatic threshold to be what it is to be. Okay. I would like to thank you here. And I didn't even touch a large part of our work. So I want to point you maybe to some interesting reading. So one is, of course, our paper on which the talk is based. I also want to point you towards the recent paper of Hong and his colleagues, which address this question of the effect of VC dimension on homomorphic threshold. And if you want to learn more about the threshold, then I want to point out to our recent work when we try to see how the min degree affects the chromatic number when you really want to find the value of this constant C. So this is relatively recent work, and it points out in many directions that you might explore. Okay, thank you very much.
Okay, thank you, Joseph, for a very interesting talk. So now we're open for questions.
Josef, can I ask some questions?
Yes, please.
Very nice talk. Yeah, so I have actually a bunch of questions. The first one would be, maybe you did, but could you explain again how, like, is there any mo reason that we consider VC dimension here?
Uh, so that was contribution of Luczak and Thomassen, who actually realized that the VC dimension is the right thing to do here, right? It's
Like, I mean, there might be another thing to quantify this, like to make this separation also work here. Like, why is VC dimension kind of natural here, or just this result says VC dimension makes the difference, so maybe VC dimension is the
what are okay, sorry. So you are asking why? Well, uh, to me, the fact that it allows you to go below threshold, it looks like it's a right thing. I mean, we found yet another condition that allows you to go below the threshold. So maybe what's
Maybe
what
good to say is that even above the threshold, right? That they observed that above the threshold, if the degree is bigger than 1/3, that VC dimension is bounded. And you right away get the bounded chromatic number just because of this results through covering. And that's what I think was their starting point, right? Just observe that for graph with minimal degree bigger than 1/3, the VC dimension is bounded. Right?
is it?
So it is, yes. I think you have some objects there that you cannot have right. So that's what they prove.
Uh-huh.
I think again, if you have a graph, triangle free graph with minimal degree 1/3 plus epsilon, I think the VC dimension is bounded. That was the starting point of this whole thing.
Are you sure? Because VC dimension is kind of a local property that you can just hide somewhere in some part of your graph. The fact that it has high VC dimension, and then the rest of the graph can just have.
Minimal degree is big, right? I thought that they're giving a different proof as a first. I mean, we can check.
Yeah, I think I don't recall. I don't remember the paper, but they do quite a bit in the paper, right? So I mean, there's Luczak.
Yeah, but this is maybe one thing to check, right?
Okay, so I have one more question regarding this general chromatic number threshold phenomenon. You said that it was studied first for K3 and then for K4 and then for general graphs. So for K3, we obviously know the exact threshold. What's the situation? What's the state of affairs with KR or general graphs? Do we kind of know, even for KR, what the exact threshold is?
Sorry that I interrupt you. Yes, so for chromatic threshold, this paper by Peter, Allen, Julia, Simon, etc., they resolve completely chromatic threshold.
And they really know the number and everything. They do, yeah.
Yes.
Okay.
Yeah. So they resolve. I mean, that's a phenomenal paper. They really resolve this question. Okay. This homomorphism threshold. That's a whole different class of the object. So for long time, we didn't even know example of one graph when chromatic and homomorphism threshold would be different, right? And I think then Maya Shankar came and finally show example that the odd cycle they differ, right? That's
I see. Okay,
yeah.
nice, thank you.
And it's like we have, I mean, for cliques they are the same. Now we have a Maya's result, and that's about it. We don't know in general. We don't know why when these two thresholds are really different, right? That's the one question that I would like to really bring up. That would be nice to decide what's really decide for H whether they have the same or different thresholds, right? And I think that's why Hong is maybe pushing this and trying to study this via this VC dimension and other techniques, just to see whether one can separate these two thresholds somewhat reasonably.
Questions? So just to understand, maybe, can you go one slide back? So what you propose, right? So this if a non-adjacent vertices have large co-degree, it's something in between, right? In between homomorphism thresholds and chromatic thresholds, right? It's kind of allows you to prove a stronger result, right? Because homomorphism threshold just says that you homomorphic to some triangle-free subgraph, which difference.
Yes.
Here you're proving something stronger. You're saying if you have this property, you homomorphic to a block, right? So it's some new parameter which is kind of interesting to study somewhere in between.
Yes. And I think Hong does, right, in this follow-up paper that he looked.
Okay, so we need to look.
Or to some extent, he studies, right?
I see.
But as I said, I mean, he looked at the cycles, and he looked to cliques. I think the most interesting part would be to look what one can say in the general case, if anything, or for some non-trivial family, and then see what one could say.
By non-trivial family, you mean graph family, right? Like
Graph
instead of cliques,
yeah.
general
Yeah.
graphs. Thank you.
More questions? So if not, let's thanks Jozef again. So thank you very much. Yeah, it was great to have you. So maybe one remark about the seminars. So if you think that you're not on the mailing list or you know other people who want to join the mailing list, please ask them to email me. And so I want to finish by saying that next week we will have talk by Sardiskin about long cycles in percolated subgraph of the hypercube. Right, a very interesting talk. So I hope to see all of you. Right, and again, the video of this talk would be available on the website of the seminar. So, Jozef, so thank you very much.
Thank you. Thank you for listening.
Oh yeah, perfect. So now I see you. Yeah, it was very, very interesting, and we will look a little bit. I think I'll check a little bit this thing. So indeed, so what did Thomassen and Luczak had? So they observed that if you have large degree bigger than 1/3, you don't contain certain induced subgraphs, kind of variant of hypercube. And that allows you to have this, at least conclusion of the, small epsilon net. And because of that, they came to this bounded VC dimension. So there it really gives a different proof of Thomassen result. So, but without any additional assumption. So if you above 1/3, you don't assume any bounded VC or anything. So you can reprove Thomassen's result just using this like epsilon, small epsilon knots for the neighborhoods, because you don't contain a certain induced subgraph. Right, so that's a kind of not containing certain induced bipartite subgraph means, I think, bounded VC dimension, right? I think they don't contain cube or something, 3 cube. So that's what I think I remember. So anyway, we can look.
Yeah, if you get anything, or if I would be very much interesting to hear from you.
But below, of course, then it's a different story. Then you need to assume, and I say interesting. Okay, perfect. So the papers which you mentioned, they're already available on arXiv, right?
They are on arXiv. There is directly,
Okay.
You are under my name, and I think Hong posted Friday last week or something like that.
Okay, perfect.
And I think there might be more coming, but
Okay, great. Thank you very much.
Thank you. Good to see you all.
Yeah. Bye-bye, everybody. So see you in a week time. We can, I guess, stop recording.